Hello class, this morning we're going to be extending our work on the vector functions. We're going to be looking at ways we can model motion of particles. One particle or maybe two particles in two dimensions using our vector functions. We want to be able to start integrating and differentiating our position function to get a velocity and acceleration vector functions. And we'd like to continue expressing our vector functions as a Cartesian equation, as a function of y of x, and start to come up with some nice formulas and equations involving vector functions that we're going to explore to model the motion of particles, of an object. These are the suggested homework exercise we're doing. Okay. Let's get into it. So, quick review of what we've looked at previously with parametric equations. We've got two functions x and y with some parameter t. Now, we want to know something about the domain and range of our y is equal to f of x. So, first off, the domain of the two parametric equations is the allowed values on t. So we've got t between some values a and b. And then important things we need to know and remember is the range of x of t becomes the domain of the Cartesian equation. And the range of y of t becomes the range of the Cartesian equation. So considering that an object moves along a path where the position vector is given by this position vector here, cos of t I in the I direction and sine t in the j direction, for t is positive. Let's state the domain and range and sketch the graph. So first off, we're going to see that the x is the function here in the I component of the vector. So x is equal to cos of t and y is equal to sine of t. Putting that together, I'm going to draw on the fact that I know a little bit about trig identities. So x squared and y squared together, and when I add them together I get 1. And I get this nice little relation, and that's in fact the equation of a circle. Now, the domain of this relation is the range of x of t. So x of t ranges from -1 to +1. And the range of this relation here, the allowed y values, is the range of y parametric equation, which again ranges from -1 to +1. And we get a nice circle with a radius 1. Okay? So let's now consider a similar position vector where this describes that an object moves along a path where the position vector is given by this. And now, as you can see, it's 3 dimensions: I component, j component, and k component. So, 3-dimensional graph. We need to sketch the graph and then describe the motion of the object. Wow, how do we do that? Consider now, we need to, sketching this graph, we need to think about a 3D dimensional plane. Well, we haven't really worked with them. It's a bit unfamiliar, 3D sketches. So an easy way of handling sketches when unsure about is pretty much plot the points. Evaluate on a table of values like this and plot a few coordinates and then join the dots. So being circular functions, we're going to choose a few radians from 0 up to 2 pi for our parameter t, and then evaluate the vector of each. And the first one there is being evaluated along these lines. Substitute t is 0 into each part, the x, the y, and the z components, and we get our values. There's our point. And I can keep going. I can do each bit, evaluate t, the position vector at each of those t's, and I get these vectors with these corresponding points on the graph. So when I plot these points, it's going to be roughly looking like this. Circle. Starting at this point. X is positive 1, Y is 0, and Z is 2. Which fits probably better right there. I'm just going to swap my axes around a bit like that. That's better. Okay. So if this is the coordinates, so when X is 1, appears down to some point here. When X is 1, when Y is 0, here on this point Y is 0, doesn't intersect anywhere along here, and Z is 2. Nicely up there. And if we keep going around the circle, we'll have when X is 0, Y is 1, and Z is 2, that's that point there. And now, the next one over here, X is negative 1, Y is 0, and so on. This one over here. And you can see we've kind of traversed this path around in some kind of anti-clockwise direction. We've started here and moved around this way in an anti-clockwise direction. So we can use that to help describe the motion, what's happening. The object is moving along a circular path, as we see, centered on right on when Z is 2, so kind of like above the ground, if you like to think of it that way, with a radius length of 1. So each time the circle is just a radius with 1 length, starting at this point and moving anti-clockwise when viewed from above, or always a distance of 2. Distance from 2 above. If we say this here, the XY plane is your ground looking straight up. Okay, get the idea? Alright, now when we start bringing calculus into our vector functions, we start with our position function, and then we can find the derivative just like this. So the derivative of the position function is the same as the derivative at the x component, the y component, the z component. Okay, so if rt is the position function, then the first derivative becomes the velocity vector function. We're going to denote that with an r dot. And then the second derivative becomes r dot dot, which is our acceleration vector function. That's the simple notation we're going to adopt. Integration is done in a very similar way. We're integrating r of t, we're integrating each x, y, and z component independently. So let's consider position of a particle is given by position function. That what is its position when it experiences maximum velocity, and what is its velocity? Well, I've got over here little what is the velocity at t equals 1. So let's start over here. We've got first, here's our from our position vector we differentiate to get our velocity vector. Okay, it's just first derivative of each expression, and then differentiate again to get our acceleration vector. And as we differentiate -3, it goes to 0, so we no longer have a j component. Now the maximum velocity occurs when the acceleration is equal to 0. Think of the maximum rate of change. Maximum rate of change occurs at something like a point of inflection. That's when the second derivative is equal to 0. So we take our second derivative equal to 0, which is our acceleration, equal to 0, and we get t equals 1. So that's the time when we get maximum velocity. Now the position at maximum velocity is we take t equals 1, substitute into our position vector, and we evaluate it, get that as a vector. Then what is that velocity at t equals 1? Well, we take t equals 1, substitute the velocity vector, and we evaluate. Okay, quite straightforward. What do you reckon? Alright, speed. Now, speed is a little different. I'll just move around with that. Speed, the magnitude of the vector of velocity. Okay, so when we take the magnitude of the vector velocity, we're determining the speed. This is not a direction, just the size only. So here's our question again with our position vector. This time we're thinking about what is the speed. Well, we worked out previously that the velocity at t equals 1, which is when the position experiences its maximum velocity, is given by that. So now, by taking the magnitude of that, I'm getting my speed. Okay, where I get 3 root 2 meters per second. And there was no units specified in this problem. Specifically, I just say put meters per second, just to denote that we must have some units for speed. Must give units. Okay. When we talk about distance traveled, we get this expression. Now, this expression for distance traveled is in fact the shortest distance between two positions, not the distance traveled along the path. So here's our position vector, and this position vector might produce a path like this, as modeled by our Cartesian equation. And you can see any 2 points, point A and point B, the direct distance between them is in fact the straight line between A and B. Now that's a little different than the actual distance traveling along this path. To find the actual distance traveling along this path is beyond our course, and we're not going to look at that. We're only going to look at the shortest distance between 2 points. So let's take our position vector. Okay, what is the distance between the particles' positions at t equals 1 second and t equals 2 seconds? So first, let's evaluate the position vector at t equals 1 second. We get that as a vector, and then do the same, evaluate t equals 2 seconds, and we get that. Once you get your two vectors, we put it into our distance traveled expression. This is, the position at time 1 minus position at time 2. It's basically finding this vector here, the black one. Okay, and then I find the size of that black vector, given by this. Okay, by taking the magnitude of the resultant vector. And I'm getting root 13 meters. Okay. Right, now we're going to stop there, and then we'll look at interaction between particles in part 2 video. Thank you.